Hello. In this video I cover a little bit my adventures and explorations in Python and Cuda. And my goal was to find a solution how to really make a kernel that covers the display area or window, and how it could be made with Python and how it could be working example. And here we see this script. Some of it I have copied from internet, and some of it I have written to really achieve my purpose. And here are several things that are important and interesting. First, we see that we import this Numba and Cuda into this script. And let's check out what this script really does. If I run it here, then we see what it looks like. My Python is running here. This is Python version 3. What it reads here, 3.9.6. And what this window does, it calculates refresh rate is 60 frames per second. And in every second it updates the data with new random work groups, or those are called blocks in Cuda. And then it detects the mouse position and displays it as a white box here. And before doing it, it fills with calculated color the canvas area. And let's close this up. And this was an SDL example. And here we see frames per second. And what this video is about, some really interesting aspects of or hard to understand problems when you start doing this first step to come up with a custom renderer or whatsoever you want to do, or game engine, or not to name more complicated programs. But we wish to have this high performance with this NVIDIA card. And here we see also in internet an example in C language how this SDL window should be set up when we wish to use this texture, dynamic texture, that we update the texture, and this is acts as a frame buffer. And I'm not a very good expert in this, because I'm just starting to explore those really deep themes. But I have experience with C and Python beforehand, but not with kernels. And let's take a look at this code here. We have this Cuda JIT. This means kernel code. And here we have Cuda JIT device true. This is a device function, and this means it is called from a kernel. And this is a positive aspect of it. What to say about those kernels in here with Numba? In this Numba module, is that as arguments we could wish to, when we are C programmers, then we wish to submit arguments as maybe some objects or arrays of structures, and with Numba this is not possible because we have a limited number of types we can submit, but not complicated Python classes, or not this. But how to overcome this problem here is that we need to dig into the data type and treat it as a data field. Then we populate with those fields of the structure elements. And for instance, if we have a structure like an RGBA color, then we got those 4 members of this structure, and here in this instance they are just 1 byte integers, unsigned integers. We here have this byte RGBA, and every one of it is initiated to the incoming color that is submitted to this device function. And before doing it, we initialize a local variable number unsigned integer of type of 8 bytes. Is it true? 8? This means all in all if I mean this is byte, but the uint 8 is how long it is. We need to check this out. Let's if it was import Numba. I do just quick test here about this type length. If I just paste this here, and this was Pythes, I mean the Python code was this. Not. How I can check this length as this string. So I have programmed in Python, but I don't remember exactly how to check this the length of this. If I search internet, Numba data types. Then we could have indication of it unsigned 8-bit unsigned byte. This is not correct here. We should have 40 uint 32-bit. Let's check out this one. But it was working, but I found maybe a first error here. Yes, this way it is working. Because it 4 times 8, and then it is 32 bit length. And then we just use this method of packing those bits into this data, those individual components with bit operations here. And we see that this from right to left in opposite direction of our thinking. This means A is first, then we handle B, then G, then B, R. And A, as we know, the notation when we look at those bytes, for example, if you got a C book or something like that, then we know that we start visualizing the single byte of 8 bits from right to left, from opposite direction of reading or Latin language, Latin-based languages. And this means that we need to submit those in opposite order. And A is the last character here, or last member of the structure, and this starts at position 0. And B starts at position 8. G starts at position 60, and R starts at 24, and covers to the end the data set, and then set 32 bit. And here I have little checks and logics to replace this color then with a mouse position here. And why it was so seemingly at low resolution, because I visualized the work groups or the work blocks here. Blocks is the name. And this was the device function here, and this device function is called from this kernel function. And kernel function then is submitted with a mouse position with this pixel array is the display or this texture that we submit. In the thinking it should be the frame buffer, but I don't know if this SDL handles it as a frame buffer, updates it in the card, or does it copy something data into a CPU memory. I don't know it. But I just follow the example in the internet here. This example makes those steps to set up those textures, and I just follow the example, and it's not in my power to just to invent something here. And but the difficult thing is how to make this example to work with this real Python thing here. And we see that first steps are the window creation here, and we check also here the free memory, and here we create this texture. The texture equals SDL2, and this is 64-bit Python 10, Python 3. And we have this very interesting and important texture format here, pixel format RGBA, and it fits into 4 bytes, 1 pixel here. And what to say about this canvas that we going to fill with those actual pixels. Then we got this very confusing nuance to this. This is involves the reversed or transposed thinking of the pixels that are submitted to form the canvas, and here we see this transposed thinking of it. We have this height first, meaning the y parameter, and then the x parameter follows it. Height is first, and then width is the second one. Everywhere else we got this width first and height the second, but with the pixel data we need to transpose it. And why is this I think is the paradigm that when we execute for instance C loops in C code, then we first the outer loop is the lines and or rows, and the inner loop the inner loop is then rows, and the outer loop is columns. Or what did I say? First, outer loop handles the rows, and the inner loop handles the columns. And columns means x parameter, the column offset from left to right, and the row parameter of y is then from top to down, and the 0 point is up left corner. And that's why it is a transposed way to define it here. But this is later we have also the same problem here in the kernel code, because for some reason those kernels are mainly used for some data science or simulations, or then we think of this like a three-dimensional cube that is subdivided into those smaller cubes. The grid it is called. But when we denote those cubes, for instance, if we have this layout for a picture surface, then we are used to think that the first parameter is x, and the second one is the y parameter. But in the kernel it's vice versa, we see here. Exactly because of those inconsistencies. And this is hard to explain, but just to warn people that those are the points of interest in those types of tasks with those kernels. And here we see that I need to compare the mouse Y parameter with block X and X parameter with the block Y. They are switched around. But if we just forget about those nuances, then it's maybe possible. Annoying sort of, but and what to say more about this code, or how to make it work. This is the next line here. Then we set this pixels array up. This is numpy array here, and we fill it with zeros and declare that this data type is numpy unsigned integer 32 bits. And we see here I made this correction that this must be also 32 bits here. This was a bug in this one. And next we declare a pointer, and this was an interesting example that I picked up in internet. And it makes a C-types use of C-type C float. And as we know, those floats fit into 4 bytes also. And then here multiplies with pixel size and creates it from buffer pixels. I cannot very precisely explain why this sort of syntax and how it works, but this is necessary for that then we submit this pointer later. Let's check out where this pointer is used. We see here we update this texture through this pointer with SDL2 SDL update texture, and we submit this pointer. And this last argument is also difficult to understand. You need to check out this documentation to come up with explanation or description for this last argument. But in this case it needs to be like this. It is the length of the single pixel row in bytes maybe. And here we do the rest of the steps: render copy, render present, and before this one comes the kernel call here, and we submit those arguments here. And what to say about those kernel measurements. This is also critical information here, because we need to pre-calculate it, and probably better programs take into consideration also the free memory that we could use, but in this case I just assume we have free memory. And here I have the trees per block declaration here, and there's is a 32 times 32 square. Then we saw this program to come up with those squares all over the place, and those are 32-bit times 32-bit squares. And in another place in the documentation, I don't remember where, I found a sentence that said that this is the maximum recommended or possible size for the two-dimensional block. And blocks in the grid size is then I saw an example that used this sale, mathematical sale function to make it better code here. And then we use this 32-bit this dimension for x and y. And this is also we see here reversed in reversed order. The y component is first and the x component comes afterwards. Or it is, we could name it as a transposed order. Then we get this color. This is a random function here that generates this color data. It is not very big data set, considering that we get those 32 times 32-bit pixels. They are not so numerous if we consider the whole canvas as pixels, then it is clearly more data there. It's like a random noise, but just this example uses only this low profile data here, and we send this numpy RI to the device with and make a Cuda color variable out of it. Number Cuda to device color. This means it is an array that resides on the GPU. And let's check out how we use this Cuda color here. Next, we check the time interval, that if 1 second is elapsed, then we just do the same thing here, generate a numpy array to the same variable and upload this to the device Cuda color. And when we call kernel, then we submit this Cuda color to the kernel. And when we press quit button, then this loop terminates, and we need to destroy the SDL structures here or objects that we created. This example is here also displays some necessary cleanup here.